To Embedded Internals. This is fifth episode of our series, Execution Awareness series. In this fifth episode, we are going to cover program execution pipeline. In the last episode, we have we have inspected inside the ELF file. Now, in this episode, we are going to check what actually happens when we run a ELF file. How the ELF file, which is a structured binary data, becomes runnable process. How a file become a process. How kernel reads it on the /elf command, it becomes a running process. This is actually a step where the kernel, shell, ELF, memory and CPU all come together. Okay, let's move forward with the complete pipeline of today's episode and how each and everything is coming together. Cell is one which is reading the command. Kernel is one which is processing it. ELF is the command which we need to require load into the memory. Memory where we are loading our ELF. CPU where all the instructions is being executed. So all these things will come together in today's episode. So let me first give you a detailed flowchart. So you give a command / to read the ELF. So cell is itself a process which is a bash shell. It reads the input. First thing it will check if it is a regular file or an ELF file or an executable. If it is an executable, it will create one new process by duplicating its own process. Okay. So our file is ELF file. So command will read it and do the fork. Fork will duplicate the process. Duplicate the current process. So the current process is shell, and now in the system two process will be running. Both are the shell process parent, which is our bash shell, and child, which is also our bash shell with the same PID. Let us take some PID value 100. Child has some its own process ID 101. Okay, parent process ID is of parent, that is 100. So we can say that shell is just a user space program. Shell is not a part of kernel. Okay, when you are giving the command on the shell, it is a part of user space program. After the fork, a new process will get created. Now two duplicate process will be there, a parent and child process, both having the same address space, same file descriptors and same environment. So here address space, file descriptors and environment, and all other details will be same. It is just a duplicate of current process. After, we don't require two process at one time, because we just require, first thing is why we need to do the fork system call. Why cannot we directly, I mean shell program will run that ELF? Because after running the ELF, after getting the output, we need the shell to continue its execution. So once the process will be killed after finishing the after finishing the code logic, process will be killed, and we don't want that. This is the reason we duplicate the current process, and in the child process, duplicate child process, we replaced our own process image. Like currently, so the second step is ELF. Now I'm explaining you ELF part. Okay, after for execve execve system, this will be called. Fork will duplicate and this will replace old image is shell with our current image. Our current image is of ELF, so it will replace the current image. So we can say before execve only shell code is being running, but after we do this replacing of the old image, now the new program, our own program, is also running. So one golden statement you need to remember is that fork just create and process, whereas execve transform the process with the new image. Okay. So what is actually happening at the execv level is when a new process is being replaced, it first read kernel verifies elf. Okay. Because elf can be corrupted. So verification is very important. So kernel verifies elf by using elf header. So first thing is to read elf header. After the elf, this step is being successfully performed, kernel loads the program header, which contain different segments. After that, it maps the memory, because without memory we cannot work. So after loading the program header, memory is being mapped, and then stack is being set up the stack segment. Stack contain some command line argument like argc, argv, and environment variables. After the stack is being set up, then entry point instruction. Now we have the stack, so we should point to the entry point. So it sets instruction to the entry point. Entry point we have seen into the elf. I will again explain you that. Set up instruction pointer to entry point. Now entry point gives a particular address. Okay, from this address you should start the execution. We got the address, so we will start the execution. So all these things is happening at execv level. Okay, this all is being detailedly explained in our episode 4, where we are inspecting elf file. You can check that if you wish. So let me show you these things from our terminal. After that we will move forward. Okay, so first step is to give the command. Okay, let us first, if you are first time coming here, so let me show you the code. This is our basic code to print hello world, to print a statement on a output device. Okay, or we can say on the terminal, or we can say on the standard output. So this is hash include stdio.h. It is calling the preprocessor directive to include on header file, which is stdio.h. This header file is being needed by the printf statement which we have used. Similarly, we have included one more header file unistd.h, which is being used by sleep system call, sleep library function. Okay, int main, where the program start execution, and this is body of the program where we have written two statement. One is to print one statement, printf hello welcome to embedded internals. Printf is a library function which will call glibc library, and which will further call the write system call inside the kernel to perform this operation. And sleep system call is to give some delay. We need to check some information, memory mapping, that's why I have given some delay. And return 0 to return success to the operating system after finishing the execution. This is our simple hello world program. Okay, after that we have compiled this program. This explanation is which I have explained in the hello world.c is uh, in depth explained in episode 1 and in episode 2. Now this is gcc hello world.c hyphen o where the compilation is being done. We have explained that in every steps whichever being performed in the compilation stage in very depth detail in episode 3. Please recheck. Now we have seen this is hello world.c. This is an elf file. Let me validate that. So we have seen that this is an elf file which is dynamically linked with the library, which is this, and some build IDs. Okay. Now when you run the command to so that the kernel will at this point of time these two files .c file and elf file are just a part of our disk, just a part of Linux. It is a file which is stored in the disk. It is not being still runnable. So when you run this command /hello world elf file, this actually become a running process. So which is our today's episode agenda. So so this is where shell is reading your command. Okay, what is happening? So first thing I told you that execve system call will replace the image. So execve system call has replaced the image. See this, replace the image, replace the elf. Okay. So image has been replaced. Okay. After replacing the image, header file will be read. It is reading some data, private, this is address, mmap, access, protection, size, libraries, all this thing is being happening. Memories is being loaded, mmap, protect segments. Then whatever functionality we need to perform, that is being done. We have used clock, so clock nanocycle with the 50 nanosecond value and the terminal. I told you that printf is a library function which get converted inside the kernel into write system call. That is happening here. So just a minute, I will execution. We get the start point, like in this case some address 0 into 1080 is our start point address. Start point means underscore start, which is not the main function. This will call the library uh, start. So libc start main, and from this glibc, library, we will have the main which we have used in our program. So we see that main is actually not the first function to be called. Uh, the first function to be called for the execution where in the elf address is underscore is we get the address of underscore start. We will look dive deeper inside this area in our next episode. How main become the what happens before the main system call, before the main function is being called. So we check the elf header, stack segments, and memory mapping, and the entry point address. One thing we also need to validate the libraries which is being used by our call. So see, this elf contain all these libraries. Okay, these all are dynamically linked library. How we can say that elf, sorry, This is DNY executable ELF. When you do file, hmm, this is dynamically linked. Okay, this is dynamically linked, and this is the library which we have been seen. So when you do LDD this, you will see how this being interrupted. This is same. This is being called from this, which is a part of this. This is a very important needed information in library, without which our program will not be called. And why I'm saying that is because when you check the library dynamic section of our ELF, you will see this. This is a shared library, which also means dynamic library, which is libc. This is libc.so.6, which is a needed, very important. Without this we will not start the execution, and its offset is this address 2d c0. Okay, so this is how we can check the which libraries is being used by our code. And why libraries are needed? Because we have to link the system calls, sorry, we have to link our library functions. Without that, ELF will not become the ELF. We will not able to create a correct ELF. ELF might have some corruption. So our program is, until linking is very important. Otherwise, program is not. We cannot say the program is actually running. ELF will not get validated actually. So these all are the part. After that, let's move back to our execution chart, flow chart. So here the start runs main, and then comes the printf. Printf is to print the statement. But we have not we didn't see the printf statement in strace. Okay, whatever code we have used is coming as write. So where the print statement goes? Why inside the kernel we are saying write a statement, write system call with our statement? Why not the printf library function? So what happened actually is, okay, when you when our function called any library function, program called any library function, this is a library function which is a part of libc, in this case glibc. Okay, this is a part of user space. Sorry, user space. Programmer knows this, but inside kernel user can not directly access kernel. So any functionality of kernel is a restricted zone. So it uh, from the library glibc will call the write system call. It's not actually directly glibc, but okay, this is a part of kernel. So printf is a wrapper of write system call, which is in the glibc library. Now this has a high execution. This system call will directly read or write, do perform the operation whichever is required by the user space. Now we can say that by using the system call, uh, kernel is working on the behalf of user space to perform the operation whatever users needed. User, because user don't have direct access to the kernel uh, runs in a very advanced mode of security. So printf get converted into write. This is called by the kernel, and that we are seeing in the terminal. We have a dedicated episode on this also in our coming episode of this series. Stay tuned for same. So this is how that uh, okay. Printf is a library function of glibc, which is the user space get called. User space cannot directly access the kernel, so uh, as a wrapper, write system call is being called inside the kernel. At this moment of time, we can say that kernel is processing on the behalf of user space. The kernel is in the process context to perform the operation whatever user has asked for. Okay. That is the reason we are seeing write system call inside the trace, not the printf statement anywhere, because printf is a part of library libc glibc, not the part of kernel. Okay, so that's why this write system call. Now after the processing, I'm moving back to our flow chart. So after printf, we get the statement a program got exit. Exit means program terminates. At what happens at the process termination? When the process terminates, exit system call is being called. What is do at the kernel level? It frees the memory whatever we have allocated. Closes all the file if any opens. Free all the resources whichever is allocated. Perform cleanup and update the process table. That is the reason after the program ends, you are not seeing the your process in your process table. So this is the complete this is what happened after the at the completion process. So we have seen that execution is not a single action. You are saying that, oh, this is a single command which we are giving and our execution is being performed, but at the back end so many things is being happening. So we can say that execution is not a single action. When we give a command shell for shell, kernel, memory, resources, cpu, everything come into the picture to execute one ELF. Execution is not a single action but a pipeline coordinated by the operating system to perform the task. I hope everyone is clear at this point of time. If you have any doubt anywhere, please write that in the comment section. If you have any suggestion, please do write it. We will include that in our coming episode. In the next episode, we are going to cover what happens before main.